Okay, so just before we start the afternoon session, I want to make a quick announcement that at the end of this talk, so around 3:30, there'll be a group photo outside for all participants. Okay, so welcome back, everyone. So I'm very pleased to introduce our first speaker for this afternoon, Ben Sharp, who's going to tell us about index estimates for constant mean curvature surfaces.
Thank you very much for the introduction. Also, many thanks to the organisers for the invitation and the ICTS for providing such wonderful facilities. So I'm going to be talking about that. It's joint work with my grad student, one of my grad students. And the general idea is that objects like CMC surfaces are often produced variationally. You might prove existence of such objects by some abstract variational principles, which will give you information on their area and their index. So it's nice to be able to relate those variational properties with perhaps their topological and geometric properties, and that's the idea of these index estimates. So we're going to restrict to two-dimensional domains, so our CMC surfaces will all be closed surfaces, and they will always sit inside some ambient three-manifold, which will be complete but not necessarily compact. So think R3, S3, H3, any quotient of those you care. Choose. And so U will always be some possibly branched smooth immersion. I'm basically going to ignore this word through the whole talk and just stick with smooth immersions. And nu is the global unit normal along the immersion U. Please just shout out if you have any questions or want to interrupt me. So as we all know, given some H in R, I'm going to say that U sigma is a CMC surface with constant H. I'm just going to write it like this. HCMC if the mean curvature vector of the immersion equals this constant times our choice of unit normal. Or equivalently, that U from sigma into my three-manifold is a critical point of the following functional, which is the area of U plus H times some kind of enclosed volume. Now, in general, there is no global formula for enclosed volume, but if you fix a homology class, then you can write one down. So I'm not going to make V explicit, but there is some kind of functional which is defined up to constant and perhaps homology class, which makes sense of enclosed volume. If you like, you can think of it in terms of, think of the enclosed volume as relative to your initial surface. So if you wobble your initial surface, there's some volume captured in between your initial one and your slightly perturbed one. If you like, that can be the volume functional. Another way of saying it is that U is a critical point of area as long as I fix the enclosed volume. This is the Lagrange multiplier perspective. Okay, so far so. Don't think I'll have lost anyone yet. So what about the Morse index? So when I say index, it's short for Morse index, which is some kind of measure of stability of our CMC surface when viewed as a critical point of some functional. So please say if you can't read my writing, or indeed if it's too big. So what's the Morse index? So let me first just define infinitesimal variation. So if V is a section of the pullback tangent bundle, then this gives rise to a two-way conversation. We get a family UT, a one-parameter family of branched or immersions. Okay, and V is just the derivative of this thing at time 0. So given such a vector v, I can construct a one-parameter family. Equally, given a one-parameter family, I get a vector v. It's, like I said, it's defined either you fix a homology class and define it to be the volume contained between your immersion and that fixed representative, not fix a homology class. You get given a homology class by you fix a representative of it. And then the volume functional is just the volume contained between you and that representative, if you like. I can, I can make that completely explicit afterwards if you like. I just don't want to heat up too much time with that now. So, and in general, for such a variation V, I want to split it into its tangential and normal component. So I'm going to write V as S plus sigma, and S is going to be the part of my variation which is normal for the surface, and sigma is going to be the part of my variation which is tangent to the surface, tangent to the image. Okay. And of course, S I can further decompose as just some function times nu, or sigma for some function f. Okay, so please bear that splitting in mind as we go forward. So this is the setup for the Morse index part. And then the sort of geometrically interesting index known as the weak index. This is simply the number of ways, so at u sigma a HCMC surface, okay, then this weak index is an integer and it tells me the number of ways we can decrease just the area of u whilst fixing the volume, or h times the volume. Okay? The analytic definition of that is the number of negative eigenvalues of the Hessian of our functional AH, so this is area plus h times volume, restricted to infinitesimally volume preserving deformations. So what does this mean? So V is volume preserving if and only if f has mean 0. So if I restrict to that subclass and count the index, count the negative eigenvalues, and the strong index, so this is weak. Oops, my writing has immediately gone small. Weak and strong is just the number of negative eigenvalues of that thing with no restriction. Okay, so in particular, the weak index is either equal to the strong index or the strong index minus 1. Okay, so if I want to understand, so the weak index is of course the thing, is the geometric thing you're interested in. Okay, it's the number of ways I can decrease area whilst fixing volume. Mostly I will be estimating the strong index, but given this, an estimate is effectively the same. Okay. So maybe I'll just write down what this Hessian looks like. So along a HCMC surface, the Hessian, this functional, is quite simple. It only sees the normal part of the variation. So that's not true. Let me write it down and then I'll talk. So this Hessian reduces to a Hessian on functions. It only sees the normal part of the variation. It doesn't care what the tangential part is doing. But the only reason I don't see the tangential parts is because I'm evaluating it at a critical point. Okay. Actually, being able to see the tangential parts will be important a bit later, as we'll see. So, you know, this is just the same as LFF, where L is the elliptic operator minus the Laplacian minus A squared plus Ricci. Should have said, this is, of course, the second fundamental form of the immersion, and that's the ambient Ricci curvature. I hope that much is clear. So, you know, the index is counting the number of ways up to second order I can reduce area at a critical, reduce this perturbed area function at a critical point. So, being able to make this quadratic form negative means that I can reduce area kind of somewhere, and you know, in the direction F. And basically you can see that having some kind of positive ambient curvature and a lot of second fundamental form makes it more likely that you'll be able to reduce area. Okay. I think that'll do for that. So let's see some examples that we've probably all seen many, many times. So first example is the unit sphere in R3. So U sigma, I'm just going to write it loosely as the round unit sphere embedded in R3 in the usual way. This is, of course, CMC. And its quadratic form looks like grad f squared minus 2 f squared. There's no ambient curvature, so you only see the second fundamental form squared, which is 2. And so you can easily read off this exercise, the weak index is 0, and the strong index is 1. It's impossible for me to reduce the area of the sphere whilst keeping the volume fixed, but I definitely can reduce its area. If I forget about, you know, the fact that I, you know, just push it in, you can reduce the area. Okay. So, as we've seen, that's the only embedded CMC surface in R3. It's also the only sphere, CMC sphere. Okay. Make some space. So far, I hope I haven't lost anybody, but please just shout out. And I will happily write down an explicit volume functional at the end. I just don't want to do it now. Okay. Next example. The, I guess, pieces of LNA surfaces. Okay, so as we all know, these are periodic cylinders, CMC cylinders sitting inside R3. And there's the unduloids, which are the embedded version. They come in a one-parameter family. And if you shift the parameter along far enough, you get a immersed version called the nodoids. Okay, but they're all CMC. Oh dear, sorry. I'm sure you know what I'm trying to draw here. Okay, and so of course they're not closed, but I'm just going to choose to imagine these things as sitting inside some. Am I going to be able to draw this? I'm supposed to be drawing it sitting inside a 3 torus, so I'm just taking a piece of it. Bear with me. Should have practiced this before, clearly. I think that'll do. Don't make me draw anymore, please. So that is obviously now a CMC torus sitting inside a 3 torus. And the Courant nodal domain theorem will tell us that the strong index of these del and A surfaces is at least twice the number of lobes minus 1. Okay, this is due to Courant's nodal domain. So I'll say that in words. So Courant's nodal domain theorem says that, didn't write this down, it says that the kth eigenfunction can have at most k nodal sets. So if I consider the unit normal along this surface, and I consider f to be, let's say that's the x1 axis, I take the first component of my unit normal, then every node gives me 2 nodal domains for the third component of the unit normal. So the Courant nodal domain, and of course, this is also a Jacobi field, right? So the Courant nodal domain theorem says that that must be at least the 2k minus 1, the 2kth eigenfunction, okay, which then tells me that all my eigenvalues before then were negative, so my strong index was at least this number here. So you can relate the index directly to the number of lobes. Of course, I'm not defining lobe, but I hope it's clear what I mean by that. Let me write this in a more suggestive way. So of course, this is approximately constant times the number of lobes, right? Which now is constant times the Wilmore energy of U. Okay, because each lobe, roughly speaking, is a quanta of Wilmore energy. Each lobe is basically a sphere, which constitutes about 16 pi Wilmore energy. So every time I go through a lobe, I pick up 1 quanta of Wilmore energy. Okay, so what is this? This thing is the integral of the mean curvature squared over my surface. Okay. So we can see that there's at least in these examples, the amount of Wilmore energy there is hanging around contributes to the instability. Okay, somehow you can, just like the sphere, you can kind of push in the sphere to reduce area. I can push in each of these lobes to reduce area one at a time, and that gives me lots of unstable directions. Oh boy, okay, so now I'm going to try and draw Wenti tori. So, third example. Please forgive this. So the Wenti tori, they basically they come with a family of lobes that look something like that. I hope you've all seen a Wenti torus before. This can't be the first time you've seen one. Okay, but they, you can think of them as kind of bent around nodoids. If you pick this thing up and forced it to make a torus, you'd end up with something like that. And so these are Wenti tori. And these, or I'm going to say Wenti/CMC tori, and examples exist in both R3 and S3. Okay, so CMC tori, which look a bit like this, exist in both R3 and S3. There exist examples with an arbitrary number of lobes, okay? By which I mean, if you give me an arbitrary number, I can find an example with at least that many lobes, okay? There exist such examples with arbitrary number of lobes. That's a very imprecise mathematical statement, but nevertheless, a result of Rossmann and for Ventitori in R3, and Rossmann Sultana for the CMC surfaces, CMC tori in S3, proved that the same is true. The strong index is bounded from below by some constant times the number of lobes, which I want you to think of as being some constant times the Wilmer energy of U. So now there's a subtlety. When we're in S3, the Wilmer energy looks like the integral of 4 plus h squared. And when we're in R3, it's still the integral of h squared. Okay. All right. All clear so far? Good. Well, I think the way I see it is kind of like you can get index, think of the sphere. You can get strong index by just going, okay? So I can do that to each of these lobes, okay? But I can also do it to these catenoid necks, okay? So, you know, the catenoid is unstable as a minimal surface. These necks look like catenoids. So roughly every one lobe gives me one squish of the lobe and one pinch of the neck. I don't know if that's, you know, fully accurate, but that's how I see it. Possibly. I mean, yeah, I mean, the same is true for the lower bound. If you want to prove a lower bounded index in terms of first Betti number, you find next to squeeze. You know, it's the same. It's slightly different for CMC because there's Wilmer energy here, right? That's being that's a different feature, I would say. For minimal surfaces, it's just necks that you want to squeeze. Don't follow that train of thought too far. So, as has just been trailed, so Capelleus has proven existence of CMC surfaces of every genus bigger than or equal to 2 in R3. And these really do look like pieces of both. He needs both the nodoids and unduloids, glues them together to create higher genus surfaces as kind of an approximate model. And then, you know, is able to perturb that to get a genuine CMC surface. I'm not going to draw those, but so a similar result, not exactly the same, but a similar result holds in S3, and this is due to the Hellers and Trides. Apologies for my pronunciation. And so, you know, we don't know what we can guess what the index is of these guys based on the way the construction is done. As far as I'm aware, that hasn't been proven. But given that these things, at least in the case of Capelleus, are constructed from pieces of Delaunay, you would expect exactly the same thing to be true. However, we also have this result of Cavalcante and Oliveira, which says that if our CMC surface lies inside R3 or some 3 torus or S3 or some positively curved space form, then the weak index is bounded from below by the genus divided by 3 plus the ambient curvature. So either 0 when we're in R3 or S3 or 1 when we're in, sorry, 0 when we're in the flat case and 1 when we're not flat. So, you know, this is kind of building on works of Ros for minimal surfaces, Sabo, and lots of other people. Okay. So, for minimal surfaces. So in the case of minimal surfaces, it's known for a larger class. This kind of estimate is known for a larger class of ambient manifolds, but we're just looking at examples right now, trying to get intuition as to what kind of index estimates we should even expect. So far, we certainly know that the more Wilmer energy there is hanging around, the more index we should expect, at least in this family. We also know that the more genus we have hanging around, the more index we have. Okay, so now I'll state my theorem. Any questions? Sorry, hello? I seriously doubt it. No. No. Nothing I'm going to say today is optimal, except what I said about the sphere, which is totally explicit. No, it's more a kind of asymptotic understanding of how variational properties relate to geometric and topological properties.
Could it be that the strong index is to number of loads minus 1?
I think I'm going to sound incredibly lazy. I mean, one could just check that, right? These are explicit. I haven't done that. I think it's highly possible that in these exact cases, but of course, these are just examples which suggest what the general estimate should be. My student is continuing this in this vein, and he is trying, well, this is a bit going out loud, so I'll tell you what he's trying to do later, but so theorem 1. This is joint with Luca. From last year, and it's very much building on the minimal case, and I'll try to clarify the main kind of technical difference, which was found by Ajiri and McAuliffe back in 2008, though I suspect both of these people knew the result was true long before then. So I'm going to write the CMC version. So I'm going to assume that my 3-manifold is a submanifold of some high-dimensional Euclidean space with second fundamental form II. And J is going to be the L-infinity norm of the operator norm of that. So in other words, at each point, I pick all tangent vectors, I plug in IIXX, take the modulus, find the largest x. That's the operator norm at that point, and then take the L-infinity norm of that over the manifold. And U from sigma n is H CMC. Then we also estimate the nullity, which is the number of 0 eigenvalues. So if I count not just the negative eigenvalues, but I count all eigenvalues less than or equal to 0, in the strong sense, then this is bounded by 60 divided by pi times 4j squared plus h squared times the area plus r, where r, I'm just going to write is the dimension of the moduli space of sigma. So 0 when sigma is a sphere, 2 when it's a torus, 6g minus 6 when it's hydrogens. Okay, let me make that explicit. So 0 when sigma is topologically a sphere, 2 when it's topologically a torus, and 6 gamma minus 6 when the genus of sigma is gamma, which is bigger than or equal to 2. So, a couple of remarks. So, of course, the example suggests that we cannot do better than bound from above by the Wilmore energy. This, right. So, when n is R3 or S3, then this is exactly the Wilmore energy of U. That becomes a 1, so it becomes 4 plus h squared times the area. We're CMC, so that's the Wilmore energy. And it's even more obvious when it's R3. So, a linear bound from above in terms of the Wilmore energy in genus is the best we could possibly do. So at least the form of the estimate is optimal, okay? In the sense that I couldn't possibly, get some kind of sublinear estimate in terms of Wilmore energy or genus, okay, because of these examples. So that was my first remark. I'm not going to write that down. But on my second remark, I'm going to say, preempt the question, 60 over pi is far from optimal. We get an explicit estimate, but just by looking at some simple examples, the round sphere in R3, you can see that this estimate is pretty bad. It's most likely far from optimal. I don't know for sure, but I suspect it's far from optimal. Okay, so as I say, this is very much building on the Ajiri-Micallef program. So let me talk about that for a minute, and then I'll state our kind of main supporting theorem, which distinguishes the two cases of minimal and CMC. So, any questions about that before I plow on? Thought I saw a hand. So, what's the Ajiri-Micallef philosophy? I mean, it's a little bit disingenuous to ascribe this philosophy to them. You'll see when I write it down, but see also Douglas, Rado, Courant. So the first step of the philosophy is to use the Dirichlet energy instead of the area. Okay, so let me just remind you. I'm going to write everything down in local isothermal coordinates, but actually these are totally well-defined. If I pick another set of isothermal coordinates, the quantities will be the same. So the area of U is, of course, just the integral of Ux wedge Uy. The Dirichlet energy is, of course, just half the integral of Ux squared plus Uy squared. And as we all know, the area is always less than the energy, and we have equality if and only if U is conformal. And when U is conformal, we also have that the first variation of the Dirichlet energy equals the first variation of the area. So, in particular, we know that U is HCMC if and only if U is a conformal critical point of EH, which is Dirichlet energy plus H times volume. Volume part doesn't change. Okay, so we have two definitions of HCMC that we can use, and we're trying to understand the second variation. And the thing that kills us, the thing that makes it hard to estimate the second variation of area is the second fundamental form squared term. So that is inherently wound up with the geometry of the surface itself. And you want an estimate which is independent as possible of the geometry of the surface. So that's why estimating the second variation of area is hard. But as we'll see, estimating the second variation of energy is much easier. It's a much nicer analytical form. But just to note, we do not have the second, at a conformal map, these functionals agree up to first order, but they definitely do not agree up to second order. So you can't just switch in the Dirichlet energy for free and keep going. You need a theorem to say how these two things differ from one another. Is it hotter in here today, or is it just because I'm giving the talk? So theorem 2. And this again is with, it's an unfortunate, our names both begin with S, but anyway. So this is, of course, due to Ejiri and Mikhailov assuming that U is minimal. Okay. But we're going to expand our horizons just a tiny bit, and I'm going to take a map into an arbitrary d-dimensional Riemannian manifold. So I know this contradicts the setup, but this particular theorem holds in greater generality. And I'm going to assume that this is a branched conformal immersion. Okay, so I'm not assuming anything about its mean curvature, doesn't solve a PDE. It's just an arbitrary conformal map. And as we know, for an arbitrary conformal map, the area and energy agree up to first order, and they're related up to second order by the following. So the Hessian. So now I can't only restrict I can only restrict to normal variations if I'm a critical point of some function, right? So we really have to compare. In order for this comparison to hold for all conformal immersions, we have to take arbitrary variations. But you can nevertheless compare these two guys, and the difference is some kind of infinitesimal conformal defect. So mu, so with the same splitting as before, V is its normal part plus its tangential part. I'll tell you what mu is before writing it down. So I'm going to use local coordinates to write it down. So the pullback metric, which is of course the thing I'm going to use to induce the Riemann surface structure on that. Oh no, I've said it's conformal. So yeah, sorry. Ignore what I just said. So I'm choosing isothermal coordinates and a local complex coordinate, therefore. Then V gives rise to a one-parameter family of variations. And the thing, so UT, and the thing which is going to tell me how so as U varies, of course, it's going to induce a new Riemann surface structure on the domain. And the thing that tells me how that Riemann surface structure is varying is if I take the Z derivative of each of these guys, that being 0 means that I'm staying in the same conformal class, staying in the same. I'm not moving the Riemann surface on the domain. Okay. So if I differentiate that quantity at t equals 0, it gives me some kind of infinitesimal conformal defect. And that quantity is that thing there. So that's what mu is. That's how mu is defined to be, it's infinitesimally telling us, so when mu is 0, then I'm infinitesimally not moving conformal class. And I can write mu down. So it's the local coordinates. I'm going to write this down. Okay. So that's what mu is. So of course, hello. Yes. Yes.
You're computing second derivatives.
Yes.
So, you know, if I teach a class on manifolds, I tell my students there is no way to have second derivatives for a function on a manifold.
Well, but then
because that depends on the charts, you know.
But then you're telling me there's no Hessian of a function on that.
Exactly.
But there is, right? You use the connection.
Yeah, but what's your connection on the space of immersion?
Yeah.
That's sort of where my question goes to. So, you know, I see when you have a critical point, of course, you can do that. Right? I see. So what you mean by it is what you're now writing. Okay, thanks.
Oops. So it's that minus that of, if you like, I take two derivatives of that in T. But in order to understand two derivatives, I need some kind of connection. So that's what I mean. That is my definition of the Hessian. And that's what you get if you try and define the Hessian on a Riemannian manifold. Like this way. And in some sense, you're right. You know, one should really try and, when I did, we spent maybe a couple of weeks thinking about that. But then we just kind of thought, well, that's our definition. This formula is true. This is all we need is for this formula to hold with this definition. But it would be nice if somebody really formalized that. We kind of define it away, if that makes sense. So as I've said, Idri and Mikhailov prove exactly the same result with the kind of equivalent quantity, but assuming that U solves a PDE. So what we do is show that this is just a general fact. For any conformal immersion, the second variations agree up to this infinitesimal conformal factor. Perhaps not unexpected, but nevertheless, I think an important fact to know. How am I doing for time? Okay, not too bad. So just to give you an idea of what the second variation looks like, an arbitrary point, you know, not assuming anything about the mean curvature. Let me just write it down. So you see both normal and tangential components. You see the thing that you expect to see. And then you see something which you probably also expect to see. And then you see some other things. Okay. So of course, when H is 0, it just gives you back what you expect to see. But in general, that's what you see. Okay, so I've actually I'm doing well for time. It's good for me and bad for you. So I'm just going to talk about the question. Yes, please.
So are you trying to construct A or E, one of them? Is it a Morse function-like thing on the space of U, or?
No, I mean, so what I'm trying to do is estimate the index of this thing here.
No, I'm asking, is a Morse function on the space of U, or?
Oh, is the area a Morse function?
Yeah.
Generically, the area is a Morse function. Yeah. Ooh. Yeah, great question. I don't know. I don't think that's known. But correct me if I'm wrong, somebody. Yeah, this is a result due to Brian White, which says that for, you know, generically, whatever that means, minimal surfaces don't have Jacobi fields. Generically, minimal surfaces don't. The second variation is non-degenerate. But that's not what I'm doing. What I'm doing here. Of course, what I am interested in is this thing, right? And that equals the second variation of area plus the second variation of volume. So that's why I'm interested in how the area moves up to second order. Okay, so I'm going to give the ideas proof, and then if there's a bit of time at the end, I'll tell you about another theorem. So the idea of the proof, once we've got theorem 2, the idea of the proof is really the Algebraic-Mikhailov idea. And it's incredibly simple and beautiful. And they're the best kind of ideas. So let's give the idea of the proof of theorem 1. So, as I promised, estimating the second variation of energy is much easier than estimating the second variation of area. So I'm just going to write that down. So the second variation of course, I'm not just interested in the energy, I'm interested in this perturbed energy. Okay. This is connection derivative of v squared minus some kind of trace over the ambient curvature of n plus h times the volume functional on n evaluated at this thing here. That. Okay. And I claim this is better. Why is it better? You know, the big quantities here only depend on the ambient manifold. The ambient Riemann tensor is what appears here. V is appearing quadratically. The ambient volume form is appearing here. Yes, we see the gradient of V, but you'll see in a minute I've just absorbed it into that. So this is really, just by a simple application of whichever inequality you like, Cauchy, Schwartz maybe it's Holder, actually I forget the names. So this is always more positive than the following shifted Laplacian. Okay. So, and of course these are now, you know, H is my mean curvature, is fixed, it's a constant. J is purely ambient manifold information. So if I can estimate the index of this shifted Laplacian, if I can estimate the number of negative eigenvalues of this thing, then I'm definitely estimating the number of negative eigenvalues of this thing, because this thing is more negative than that. Okay, so I'll leave the theorem up. Yeah. That's right. Yeah, so that's right. That's right. Good question. And that won't be clear from what I'm about to say. Sobolev. Yes. Absolutely. Yeah, this is a common theme of this kind of game. So there are, yeah, you know, you would then minimize J squared over, that's right. You'd want to do that. That's right. Find the best embedding possible. Yeah, exactly the same thing happens proving index bounds from the other side. You kind of have to embed it in somewhere, usually Euclidean space, to construct test functions. And then you get extra noise from the embedding in your calculations, which you want to minimize. Okay. All right. What are we doing? So estimating this, so this is now in effect a shifted Laplacian, and counting the number of negative eigenvalues of a shifted Laplacian can be done as long as you have a Sobolev inequality on your domain. Okay? And by embedding everything into Euclidean space and knowing that it's CMC, I do have the Michael-Simon-Sobolev inequality on my domain, so I can estimate that shifted Laplacian. And what you get is that the index, the strong index of the energy plus the nullity of the energy, is bounded by this, the thing we wanted. Okay. But theorem 2 now implies that the Hessian of the thing I'm trying to estimate is just the Hessian of the thing that I can estimate minus this conformal defect. Okay? So if I, so this is now fully Ijiri-Mikhailov. So if I restrict to the class of immersions which fix the conformal class, then they're exactly the same, right? There's no defect, okay? So in other words, I'm gonna write it like this. The Hessian of this restricted to the conformal class is just that, restricted to the infinitesimally conformal variations. So if I, first of all, estimate the index, so if you like, the index of AH plus the nullity of AH restricted to the conformal class is bounded by, restricted to variations which don't move the conformal class, is bounded by this quantity. But what's left? So I now have to restrict to the variations which change the conformal class. Okay, I've started with the variations which fix the conformal class. I know that in that world, I've already estimated the index. I now look at the variations which move the conformal class, but I don't really care what they are. I know how to estimate the whole space of variations which change the conformal class. That's at most the dimension of the moduli space of sigma, which is R. So of course, formalizing that takes a little bit of work. You have to analyze this PDE here. You're sort of interested in when solutions to this, given an S, when solutions to this in sigma don't exist. And you can't make that to be 0. And of course, when you run the numbers, you get the dimension of the moduli space. So that's the idea. Then you just sum those things up and you get the theorem. Do I actually have any more time? 2 minutes. So I'm just going to write one more. I'm just going to write one more theorem, and then I won't say anything more. So in fact, I'm going to remove what I've just. No, I'm going to remove. Apologies for my board etiquette here. It's not a very good example, but never mind. So you can just sort of check by eye that these estimates are really bad in the setting of negative ambient curvature. So if you're in hyperbolic 3 space, you take the CMC sphere and just grow its radius ad infinitum, then that thing always is weakly CMC stable, but its Wilmore energy is going to infinity. Okay. So the estimate is really bad in the presence of negative curvature. So we nevertheless prove, yes, this is 3 now, that if N3 satisfies, if it does have strictly negative curvature, So these are the sectional curvatures. If they're always bounded from above by some negative number, and the mean curvature of my HCMC surface satisfies, well, it's sufficiently small in terms of the upper bound of the sectional curvatures, then either one, the strong index plus strong nullity is bounded from above by this purely topological quantity, or U is totally umbilical, totally umbilic. And we are CMC strictly stable. So unfortunately, this theorem still doesn't apply to spheres in H3, but it nevertheless is still a theorem which holds in the presence of negative curvature. And I will stop there, Jason. Thank you.
Thanks very much, Ben, for that very nice talk. Are there questions or comments from the audience?
Yeah, thanks for talking. I had a question related, I think, to what Franz was asking about.
Yeah.
So in the first theorem, is there a version of it that's like in terms of the intrinsic geometry of n and not in terms of the immersion? Maybe you commented on this already, or
Not that I know of.
okay.
No. Sorry?
Do you think there could be, or
I mean, I have no reason to believe why not, but I wouldn't know where to start. So yeah, Jerry Mikhailov effectively, of course, for them H is 0, and this whole constant for them, they also embed everything to Euclidean space, and this for them is just some constant which depends on the isometric embedding of, you know, it's a similar thing. But yeah, it shouldn't depend on an embedding of the ambient manifold. Right.
Hello, the number 1 over there. In theorem 3, number 1, what is eta s and r? Sorry, I missed all that.
So the strong index plus nullity of my CMC surface is bounded by the dimension of the modular space, purely. Exactly. So it's either 0 if you're a sphere, it's 2 if you're a torus, or 6g minus 6. So in other words, it's a purely, so the general estimate has this Willmore term, but in the presence of ambient negative curvature and sufficiently small mean curvature relative to that, the bound is, you can forget Willmore, doesn't feature. Well, I call it a Willmore type energy because it
square minus. Yeah, right. Here
That's
you
right.
said it's 4 plus.
That's right.
Mean curvature and hyperbolic space, it would be h
But
square minus.
of course, the form of this involves me taking H3 and embedding it into Euclidean space, which is of course madness, right? So it would still be, you know, as you say, yeah, it should count
This
against.
embedding is pretty grim, right? Hyperbolic space needs.
Yeah, yeah. No, I'm definitely not recommending.
Here.
So this theorem, I suppose what I'm trying to say is this theorem is strongest in positive curvature. That's what I'm trying to say.
Then you have the second.
Then that's right. That's what I was trying to.
Yeah.
And yeah, so this one doesn't need an embedding anyway. Or maybe it does. Sorry, forget that.
I have one question. Why 60 over pi?
That's the constant we get. So we get some horrible, you know, at some point we have to apply Young's inequality with a delta, and we get an estimate at the end, and then we optimize in delta. You can't optimize explicitly in delta, but you can plug in a few values, and I know that the constant, whatever I get, is less than root to 40, at least for some value of delta. I plug that in and get 60 over pi. So yeah, it looks nice, but it's yeah, it's just an arbitrary constant. Yeah. Yeah, so there, the index there is known to be bounded from below by the genus. I think capital A has explicitly computed index of those, and it is in terms of the genus.
For the Lawson surfaces, I think he's done it. Is that
No,
the
he's
number?
computed.
It's just the number, just the
Yeah.
number, yeah.
There's some formula involving the genus.
That's quite recent. David Weigel. But yeah.
And maybe also the, yeah,
Yeah.
I need to look that up, but that exists, yeah.
Okay, that's a great number of questions. Let's thank Ben again.